Okay, everybody. So now we're not really switching gears, but getting into the core of the Dream Challenge this year. So we'll first start with the olfaction prediction challenge. We've heard a lot about olfaction, so maybe the ones that didn't know anything about it, now you're really into it. Things are happening in olfaction. It's kind of an interesting field. I'm going to discuss a little bit, just introduce the challenge and how it kind of came up, how we thought about doing this. Um, so I guess around around 10 years ago, more or less, yes, when I started working on olfaction, I think there were three things that I thought were really interesting, and we should try to see how good we were at. One is, can you predict how something smells from the structures? So that was the first challenge. This is this is what we did. So the idea was, we have these like great data set from Leslie and Andreas that Joel showed. And so we divided these 476 molecules into a leaderboard set, a training set with the majority of the molecules, and then a hidden test set. We find that leaderboards are actually really nice for people to see how well they're doing and to incentivize, discussion in the boards and things like that. We gave them the molecular features. Back then, there were these dragon features, which are now obsolete. So now there's a bunch set of new features, including the principal olfactory map that Joel showed. And you could use all types of features back then. So that was the first challenge. The second thing that, and thanks to that, what we could for the first time really kind of from molecular structures predict these sets of descriptors. The second thing that I thought was really exciting out of this challenge is that, as Joel said, people used to just try to predict pleasantness and intensity. They just thought that descriptors were just maybe too unstable. And although there is some of the truth on that, right? Like Joel showed, some people describe things on one way with some words or with another. One of the things that we did is use word embeddings back then from Word to Vec. Now they're much better models to predict what other things smell like. So you could have a more complex description of smells. And the third thing was really, can you try to predict what mixtures smell like? Now, it's very difficult to have a data set that has descriptions of mixtures, right? Because it's just too large. It would take too much money to collect something like that. And it doesn't exist. Maybe, as was asked by Benjamin, companies, have those types of data sets, but really is their secret sauce. And also, descriptors are used in a very different way. If you are in the beer industry, if you are in the marijuana industry, if you are in the perfume industry, if you are, Coca-Cola industry, like words are used in a very specific way. And it's very hard, even or wine industry, between specialists to agree on the description. They seem to be very specific to fields. That's one problem that we find. But there's a cool way of trying to measure how mixtures, how similar two mixtures are. And this is the discrimination test that you see here. So you have three mixtures, and two of them are the same. Generally, the ones that are the same are at a different dilution, so that there's a little difference, but not in the essence of the smell, but more in the concentration. And then there's a third one that's different. And then what you ask participants is, can you distinguish which one is the different one? And so for a particular set of mixtures, of two mixtures, you get a percentage of people that are able to discriminate or not the mixtures, and that kind of gives you a distance. So it's kind of a nice, very nice and simple way for doing that. So what was nice also is that there was a public data set, kind of historical public data set, that basically had three publications: the Snitz, Bush did, and I mean, I think those were the main, the bigger ones with the most data. And now Bushdid was a data set where in a very specific way they would change the composition of the mixtures So there are more and more different. So they're really kind of trying to build a ruler to try to understand the mixtures. And that led to the paper, the famous paper of the trillion other discrimination, where they showed that humans actually are really good at discriminating smells. So if I tell you, can you say what this smells like? You're not going to be very good at it. Only 25% will guess what something smells like. But if you try to discriminate between others, we're very good at that. So it's a little bit like, perfect pitch and distinguishing between two notes, right? It's very difficult to know without the reference what a note is, unless you have perfect pitch. But distinguishing between two notes, even if you know nothing about music, is actually pretty easy. So this is exactly what happens in smell. So given that we have this public data set, 700 pairs of mixtures from 3 public data sets and about 600 unique molecules, the SNITS data set actually is very particular because the Bushseed data set had mixtures that had 10, 20, or 30 molecules inside it, and they would compare them based, 10 with 10, 20 with 20, like that. SNITS is very different because they had some mixtures that had 30 molecules and others that had 1 or 2, or it was kind of very diverse. So those 2 data sets really helped having somehow a diversity on the types of molecules that we could use. Now, as we said, to do a DREAM challenge, you need a test set, so something that has not been published. If not, it becomes impossible to really evaluate the people. And in discussions with Andreas Keller and Leslie Voskhal, it turned out that they had a test set of 46 pairs of mixtures that they had built in their lab, and they really, didn't really know what to do with it. And what was this data set? Well, what they thought of was, can we try to build metamers, which is something that, what's also Noam Sobel tried to do, and apparently for a couple of mixtures, they were able to do that. So what's a metamer? A metamer is 2 mixtures of molecules that smell the same, that are indistinguishable, but that have no molecules in common. So can you basically do 2 others that smell the same, but have no molecules in common? That was the idea they wanted to try. And so how they did that, they were like, oh, well, Andreas and Leslie are very good at, they know a lot about smells. They were like, well, let me just think about mixtures of things that I think will smell the same. And let's do a data set, and let's try it with a bunch of participants. And so this is what you have. Sorry. Oops. This is what you have here on the right. So you see each of the mixtures. So I'm having a problem with the pointer. Here. Thank you, Seth. Maybe I should know where the pointer is, but okay, I was trying. Okay, sorry, couldn't read that. Okay, thank you. All right, so basically they set up a pairs of mixtures that they thought were gonna be very similar in smell, but that had no molecules in common. And as you can see from the percentage of correct of distinguishing, they weren't really able to do it, right? Except for maybe these 2 here at the end, which start to be close to the random choices, which is 33%. Mixtures were pretty different. You can see here also, like they asked participants how sure they were about their response, and most of them were pretty sure. Of course, here you see that those 2 really seem to start being kind of similar. As a control, what they also did is they just decided to have random pairs of mixtures and see, if you basically select just through knowledge or make a random pair of mixtures, would you see a difference? And you can see that it's true that with the random pairs of mixtures, there seems to be a little difference, right? More higher percentage of people were able to differentiate them. But still, it's not close at all from random choices. So this is kind of one part of the data set. And by the way, this is the first time I publicized this. The second thing they did, and I guess this is a picture of Andreas kind of putting his robot hat, although I don't know what he was doing there, but probably smelling something blindly. Or Andreas has a gallery in Chinatown that's on things all related to smell. So if you ever go to New York and you're interested in smell, go see his gallery. He always has interesting kind of strange of things. So what he did is he decided to actually take the Snitz model and calculate pairs of mixtures that would be close based on the first model that was shown to be, predictive of mixtures being close. And when he did that, again, he again did some random choices, and then did all these different mixtures. And again, he didn't see really, a big difference. None of the mixtures could really, all well distinguishable. And then he just took again the two from the previous experiment and just checked again that indeed these were pretty similar. Were the only two that seemed to be pretty similar. So I guess in a way it's kind of a failed experiment. I mean, they were trying to get things that smell the same and they couldn't really do it. So it really shows that it's not as easy, right? It's not as easy to just be able to build this metaverse. But luckily, this is an unpublished data set, and this is what we decided to use for our first challenge. It seemed to be diverse enough, was trying to explore the space. They're both kind of controls, random mixtures, and things that should smell very similarly. So it just, seemed to be a very nice data set for the challenge. Now, we only have 46 mixtures, so of course that's, it's kind of a small test set compared to sometimes other challenges or to what machine learning competitions usually do. So I just want to show you the results of the challenge. So in a way, it was a successful challenge because 28 teams participated, so a little bit more than in the previous challenge. We ranked them following two metrics. On the right, you have the mean square error. So basically, the distance that you predicted that the two mixtures were going to be and the actual distance that was measured. And then on the right, you see the correlation between your prediction of the distance between the two mixtures that from the 46 and the actual value. And so if you can see here, it seems that the first team here from Aaron Ravia and Noam Sobel's team seem to be clearly a best performer compared to the others. In the two metrics, they rank first. But one of the things that we do in DREAM is we like to be sure that this is robust. And so what we do is we took 10% of the test set randomly. So from the 46, we select four of the mixtures and add them to the test set in order to now calculate the score based on 50 pairs of mixtures instead of 46. And that, as Gustavo says, you're just modifying a little bit the test set, right? You don't want to modify it too much. You just want to see how robust it is if you change a few of them. And we repeat this thing 10,000 times. And when we do that, we get a very different picture. You see the error bars are actually, pretty high. And so if you do, how we selected the best performer was we do a rank sum of the two metrics. And for each of the folds of the data set, you count the number of times that a team ranks first. And what we saw is that the first four teams basically were tied. They, out of the 10,000 times, they all, 2,500 times, one of the teams ranked first, and that was divided in four. So basically the first four teams here, in both, when you rank both metrics, were tied in the number of times that they were first. So really, we couldn't distinguish between these first four teams when we do this little bootstrapping. And so here, the final results are that we got 4 teams that were tied in first place. Bell Faction, that's the team from that comes from the University of Leuven. And by the way, one of the presenters is on its way. He's on a bus from Chicago to Madison, so hopefully he will make it at the end of the session. Then a team from Nice, from the University of Nice, ChemSense SimLab. D2Smell, which is a conglomerate of teams from Yale, from Aaron and Noam Sobel's team from Israel. That's D2Smell. And then I guess the local team, which is the team from the University of Michigan, Kazi, that also will be presenting today. So what's interesting about these 4 teams is that they all used very different approaches for trying to solve the problem. The team from Leuven, and you will hear more about it, used kind of like the word embeddings. The University of Michigan used the principal order map embeddings. The lab from Paris used more like fingerprints, and D2Smell used a set of mixtures of different ensemble models. And all of them basically were indistinguishable, which really tells you that we've reached a point where it seems that we need to find larger data set, or different variables, maybe different concentrations, or a different way to measure the distance between the mixtures, because really we couldn't really distinguish the teams. And the fact that they were using very different features and very different methods. So that's what it's really interesting. So in a way, we've reached a point where we cannot go further than that. One of the things that we always do at DREAM is we try to do the wisdom of crowds. And so how we do that is, well, we aggregate the predictions from all the teams into, if you want, a wisdom of the crowd prediction, just by averaging the predictions, the distance between the mixtures. And that's what you get. That would be this team here. So it's a team composed of 28 teams. And then we do that with the first 27 teams, 26, etc., until we just do the aggregation between the first 2 teams. And what you can see here in both metrics, so you have the correlation in black and the distance in red, is that in this case, aggregating the solutions didn't give a better solution than the best performing team. If you remember, the best performing team had a correlation of 1.6, and and the distance is not lower than that. So really, even it really seems that although the teams are using a diverse set of features and a diverse set of approaches, the diversity is not large enough to give a better result. So it's one more proof that really we've somehow reached the maximum of our knowledge with this type of data set for this type of predictions. The fact that the wisdom of the crowds, even between the first 2, 3, or 4 teams, doesn't really add to the result. So that's again a kind of an interesting conclusion from this challenge. So before just going to the credits, I want to say that also something that happened in this challenge, and this is, I want to also make it public. This is something that, I didn't want it to interfere with the challenge itself, but for five teams downloaded the gold standard by mistake. So there were some problem in Synapse that suddenly you could download all the data sets, and the test set was in there. We realized that pretty rapidly, so only 5 teams did that. And we emailed them right away. We told them, you have the test set, just don't use it, because you're just gonna mess up the challenge. And luckily, that didn't happen. So actually, one of the teams, the D2Smell, downloaded the data set, so they're one of the 4 best performers. So we contacted them when we saw the results, and we asked them to send the code, first of all, to acknowledge if they had used the test set or not. They said they hadn't in a direct way, that of course they saw they had it, but they didn't implement it in the algorithm. And then they give us their code, and we checked that, of course, the file was not used, and we could reproduce the results with their code. It was a little bit of work, the code was not, but we went through that in order to be sure that the results, are kosher and objective. So those are the types of things that can happen. This is really the first time I have a mistake like that, where you just straight download the test set. but we're happy that we could go around it, and I'm happy to answer questions if you have around that. Okay, so I just want to give the credit to Joel Mainland. I mean, he's the one who got the funding for organizing this challenge and another one. So hopefully next year we'll organize a second round that would be as exciting. Maybe we'll push the borders through getting more data or through getting different types of mixtures or etc. Leslie and Andreas for having the data set. They had shared to me the data set a few years ago, but really didn't know what to do with it. And so, one day I just thought, well, I mean, we have the money, we have the data, why shouldn't we try this challenge? And I think it was really a success in that way, in that we got an answer to how far can we go in the state of the art. And finally, Gaia Andreotti, who helped doing all the scoring. It's always a lot of work. There's always, problems and little details that are very important for being objective about this. Verena and also that also helped with some of the initial scoring, and Jake Albrecht from Sage, that used to be at Sage Bionetworks, and that helped organize this challenge. So with that, just want to thank everybody for being here and for being interested in this challenge. Thank you.